A-level mechanics, problems involving three forces, Lamis theorem and concurrence. There are two results we can use when we're trying to solve a problem involving the equilibrium of three forces. One of them is Lamis theorem, which is not usually included in the A-level syllabus, but it does give a very quick way of solving certain problems and is very easy to use and remember. Suppose we have three forces, capital A, B and C, in equilibrium at angles little a, b and c, with angle little a opposite force capital A, angle little b opposite force capital B, and so on, as in the diagram. Because the forces are in equilibrium, we can draw them as a triangle. So if we draw the force A first, where it ends we begin force B, where B ends we begin force C, the end of C will then join to the beginning of A. We can then mark in the known angles. If we extend the side A, we get the angle between A extended and B is C in the original diagram. If we extend the line B, we get the angle between B extended and C is A in the original diagram. And if we extend the line C, we get the angle between C and A is equal to B in the original diagram. Now that means we can then fill in the angles in the triangle. And they are 180 minus A, 180 minus B, and 180 minus C. So we can then use the sine rule in the triangle. A over sine of 180 minus A equals B over the sine of 180 minus B equals C over the sine of 180 minus C. But we know the sine of 180 minus A is the same as sine A. Sine of 180 minus B is equal to sine B, and sine of 180 minus C is equal to sine of C. And so we can write A over sine A equals B over sine B equals C over sine C. This is Lamis theorem. In the original diagram, we write down each force over the sine of the angle opposite it, and these are all equal. Lamis theorem is very similar to the sine rule, but it involves three forces and the angles between them, instead of three sides of a triangle with its angles. As an example, in the diagram, find the forces F and G. Now to solve this, we use Lamis theorem. F over the sine of the angle opposite, which is 130, equals 11 over the sine of the angle opposite, which is 160. If we multiply both sides by the sine of 130, we get F is 11 times sine 130 over sine 160, which tells us F equals 24.6 newtons. Now we can work out the angle that's missing in the diagram because the angles add up to 360. So the angle opposite G is 170 degrees. So, using Lamis theorem, G over the sine of 170 is 11 over the sine of 160. If we multiply both sides by the sine of 170, we get G as 11 times sine 170 over sine 160, which works out to be G is equal to 5.58 newtons. This method is much quicker than resolving forces or even having to draw out the triangle of forces, but it only works if we have exactly three forces. There's another thing worth bearing in mind when dealing with problems involving three forces. Concurrent forces. If a body is in equilibrium when exactly three forces are acting on it, then the forces will be concurrent. That means they all pass through a single point. To show this, suppose the forces are not concurrent. Then consider a point where two of the forces intersect. The third force will not pass through this point. This means the third force will try to rotate the body around the intersection point, so the body will not be in equilibrium. Now this is not possible because we're told that the forces are in equilibrium, so the forces must be concurrent. Let's have a look at an example. The diagram shows a sphere with radius r and mass 2 kg attached to a light string at P. The string has length 1.5 r and is attached to a smooth wall at Q. The sphere rests against the wall. In part A, we're asked to find the tension in the string. Well, to solve this, let C be the centre of the sphere. Then the weight, 2g, acts through the centre of the sphere. The normal reaction R will act through the centre of the sphere as well. This means the tension T must also act through the centre of the sphere, because three forces in equilibrium must be concurrent. So Q, P and C must all lie on the same straight line. Now CP is equal to R and PQ is equal to 1.5 R, so CQ is equal to 2.5 R. Also, CA is equal to R, and we have a right angle at A. A tangent is always at right angles to its radius. Let theta be the angle the string makes with the wall. So, sine theta is equal to R over 2.5 R, which cancels down to give 0.4. And so theta is the inverse sine of 0.4, which is 23.578 degrees. So resolving vertically and marking angle theta, we've got t cos theta equals 2g, or 2 times 9.8. So t is equal to 2 times 9.8 over the cosine of 23.578 degrees, which is equal to 21.385 newtons. Now in part B, we're asked to find the reaction at the wall. Now if we resolve horizontally, the angle between T and the horizontal is 90 minus theta. So we get R is equal to T cosine of 90 minus theta. Resolving is always the force times the cosine of the angle between the force and the direction we want. So R is equal to T sine theta. So R is 21.385 times 0.4. which works out to be 8.554 newtons. And so our answer is the tension in the string is 21.4 newtons, and the normal reaction R is 8.55 newtons. The following exercise has two questions. Pause the video at this point and have a go at them yourself. When you've attempted them, restart the video and I'll go through the solutions. Okay, let's see how they're done. In question 1, we're given that a mass of 1.5 kilograms is suspended from two light strings at 10 degrees and 20 degrees to the horizontal, as in the diagram. In part A, we're asked to find the tension in string AC. Well, to solve this, we first need to draw a diagram. And then in the diagram, mark in the forces and the angles between them. Well, to start with, we've got the weight of the 1.5 kilogram mass, and that's 1.5 g. Then we've got the tension in the string going up to A, we can call that S, and the tension in the string going up to B, we can call T. Now the angle opposite the weight is 150 degrees. We can see that angles in a triangle add up to 180. The angle opposite the force S will be 20 plus 90, which is 110 degrees, and the angle opposite the force T will be 10 plus 90, which is 100 degrees. So we can then use Lamis' theorem, and that says S over the sine of the angle opposite, so that's S over the sine of 110 degrees, is equal to 1.5 g over the sine of 150 degrees. Well, g is 9.8, and if we multiply both sides by sine 110, we get S is 1.5 times 9.8 times the sine of 110 all over sine of 150, which works out S is equal to 27.627 newtons. Now in part B we're asked to work out the tension in the string BC. Well, again we can use Lamis' theorem. Now we have T over the sine of the angle opposite it, which is T over the sine of 100 degrees, is equal to 1.5 G over the sine of 150 degrees. Now G again is 9.8, and we can multiply both sides by the sine of 100 to get T equals 1.5 times 9.8 times the sine of 100 all over the sine of 150, which means T is equal to 28.953 newtons. So we get the result. The tension S, which is in the string AC, is 27.6 newtons, and the tension T, which is in the string CB, is 29.0 newtons. In question 2, a uniform rectangular lamina of mass 1 kilogram with length 60 centimeters and width 40 centimeters is suspended from its top corner. It's pulled to the side by a horizontal string connected 30 centimeters down the opposite side. It rests with the top horizontal as in the diagram. Find the tension in each string. Well, to solve this, the first thing we must do is draw a diagram and mark in the forces. Now the first force is the weight, that is 1G, or 9.8 newtons, acting vertically down from the centre of the rectangle. We can then draw in the force acting on the top corner and mark it P. And we can draw the horizontal force acting halfway down the side and call that Q. Since there are three forces and the lamina is in equilibrium, the three forces must be concurrent and all pass through the same point. Now, if we extend them, both Q and the weight pass through the centre of the rectangle, and so P, extended, must also pass through the centre of the rectangle. If we mark in the angle P makes with the horizontal as theta, we can see that we've got a triangle with sides 20 and 30 centimetres, so the tangent of theta is 30 over 20, which is 1.5, and so theta is the inverse tangent of 1.5, which means theta equals 56.31 degrees. We can now use Lamis' theorem to calculate P and Q. Well, the first thing to notice is the angle opposite the weight is 180 minus theta. So we have P over sine of 90 equals 9.8 over the sine of 180 minus 56.31. And this gives us P is equal to 9.8 times 1 over the sine of 123.69. And we can work that out to get P is equal to 11.778 newtons. Now we can also notice the angle opposite Q is 90 plus theta. So Q over the sine of 56.31 plus 90 is equal to 9.8 over the sine of 123.69. So Q is 9.8 times the sine of 146.31 over the sine of 123.69. Well, we can work that out to get Q is equal to 6.533 newtons. So we have the two forces P is equal to 11.8 newtons and Q is equal to 6.53 newtons.